Okay, in this video we're going to learn about thermodynamics. The two key learning goals for you, the viewer, are for you to be able to first define and explain free energy and its relationship to both reaction kinetics and the equilibrium constant. And second, for you to be able to predict when reactions are thermodynamically favorable and spontaneous, or on the other hand, unfavorable and not spontaneous. So let's get started with the concept of Gibbs free energy. So Gibbs free energy is a concept from physics. It's the amount of energy available to do work. In biochemistry, that means Gibbs free energy is the amount of energy available to power other reactions. And we usually talk about the change in free energy during a reaction, and that's denoted by delta G. This is the Greek symbol delta for change in G, Gibbs free energy. So we're going to be talking about delta G, change in Gibbs free energy. When delta G is negative, that means that energy is released by the reaction, and so that free energy is available to power other reactions, and the reaction can therefore occur spontaneously. So we have an excess of free energy available when we have a negative delta G value for a reaction. So the change in Gibbs free energy in a reaction is determined by a few different factors. There's the change in enthalpy, that's the heat of the reaction, the change in entropy, or the disorderedness, and then the temperature as well. So the relationship here is captured by this equation, which is delta G, the change in Gibbs free energy in a given reaction, is equal to the change in enthalpy, or the heat evolved in the reaction, minus the change in entropy, delta S, multiplied by the temperature, and that's in degrees Kelvin. So basically the two things that are going into defining or determining the change in Gibbs free energy are the enthalpy, or heat change in the reaction, and the entropy, or disorder change. And the entropy also has this temperature term, so temperature will affect the free energy of a reaction. So again, delta H, the change in enthalpy, is the heat evolved, or the enthalpy generated during a reaction. Enthalpy is another term for heat. Delta S is the change in entropy, or disorderedness. So a reaction is generating more disorder, going from one molecule to two. There's more ways to arrange two molecules in space or in solution than one, so that's an increase in disorder. So as you go to an increase in disorder, you favor more free energy. As you have more heat evolved, like think of an explosion generates a lot of heat, that's a favorable spontaneous process. And again, T is the temperature in degrees Kelvin, so at higher temperatures this favors generating a more favorable reaction, more delta G, more negative delta G. So let's think about the relationship there again, because this is key to understanding change in free energy in a reaction in terms of these two parameters. As we have more disorder, there's an increase in delta S. So that could be if you're generating a gas during a reaction, or again going from breaking a molecule into two pieces, one molecule going to two. Anytime you have more disorder, you're going to have an increase in S, delta S. So you're going to have more disorder. And because there's a negative sign in front of delta S, that ends up making delta G more negative, because we're subtracting this value from delta G. So more disorder means a more negative delta G, means a more favorable reaction. Now delta H, if we have a negative delta H value, enthalpy, that means that we're evolving heat. We're generating more heat. There's an excess of heat in the reaction, and again that's going to favor a negative delta G and a spontaneous reaction. So again, you think of a reaction that's generating a lot of heat, like an explosion, that's negative delta H, and therefore usually a negative delta G. So a positive delta S value promotes a spontaneous reaction. A negative delta H value also promotes a spontaneous reaction, because both of those lead to a more negative delta G for a reaction. Now, there's another important relationship between Gibbs free energy and the equilibrium constant for a reaction that tries to capture this concept I've been mentioning of whether a reaction is spontaneous or not. So remember, the equilibrium constant, back from general chemistry, describes the equilibrium between products and starting materials for a reaction. So if you have a large equilibrium constant, a large number for an equilibrium constant, that means the reaction favors the formation of products relative to starting material. If you have a small equilibrium constant, on the other hand, then the reaction is unfavorable and it favors the starting material. So we can apply, you can see how that relates to delta G, because a reaction that favors product formation, having a large equilibrium constant, is going to, therefore, we would think, have a negative delta G value, because that would also be a reaction that promoted product formation, was favorable, and ultimately spontaneous. So we can think about this another way. If a reaction is at equilibrium, meaning there's no net product or reactant formation, so we would say it's at equilibrium, the equilibrium constant, based on the way we define equilibrium constant, is exactly equal to 1. So that's a reaction at equilibrium, no net product or reactant formation. Equilibrium constant is 1. Well, we just discussed delta G, and in this case we would see that yes, delta G here would not be positive or negative, it would actually be 0, because there's no driving force for the reaction to either generate products or starting materials. So when the equilibrium constant is 1, the delta G value is going to be 0. So we can actually capture that relationship in an equation, and that's shown here. And this will hold for any value of equilibrium constant and any temperature. And temperature, again, is in degrees Kelvin here. So the relationship is that delta G is equal to, exactly equal to, the natural log of the equilibrium constant multiplied by this factor, which is R is a constant and T is the temperature. But for a given temperature, this is not going to change. It's just going to be negative RT, so a number, whatever it is, multiplied by the natural log. And because there's a negative sign here, if we have a positive, large positive equilibrium constant, we'll take the natural log of that, and we're going to still have a positive number, and then multiplied by negative RT, that's going to give us a negative delta G. So a large positive number here is going to give us a negative delta G, just the way it makes sense intuitively. Now we can test this case we just discussed. What about a reaction at equilibrium? So if we have an equilibrium constant exactly equal to 1, we could substitute a 1 here. Now remember your log function. The log is, natural log is what e to what number would generate, raised to what power would generate 1. And so remember that's 0. So the natural log of 1 is equal to 0. And we multiply RT times 0, we get a delta G of 0. So in other words, when we have an equilibrium constant of 1, we can see that when you take the natural log of 1, you get 0, and so there's no delta G value for that reaction is 0. No change in Gibbs free energy. So that's an important relationship to remember. And another way to think about this relationship is that as you increase the temperature of a reaction, you're going to generate a more negative delta G value. Now we saw that on the last slide as well, that because of the negative T delta S equation, the more higher temperature also there favors a more negative delta G, and we can see the same thing here. Now similarly, as I mentioned, a larger equilibrium constant, so a reaction that is really driving product formation, there's a equilibrium vastly lies way in the favor of product, is going to then have a very large equilibrium constant, let's say, still a fairly large natural log of that, and then multiplied by negative RT, we're going to have a negative delta G value. So reactions that favor product formation are going to give us that negative delta G value. Okay, so with these concepts in hand, let's try to test yourself. So take out a sheet of paper and write down these 3 examples. A case where you have a reaction with an equilibrium constant greater than 1, equilibrium constant equal to 1, and equilibrium constant less than 1. Okay, so you can pause the video, take out a paper, write those down, and now I want you to write next to each of those, what does that imply about the delta G value for that reaction. Okay, so go ahead and test yourself first. That's always a good way to see if this is making sense, rather than just listening. Pause, try to predict the delta G value for each of these reactions, and then come back to the video and I'll tell you what the answers are. Okay, so we're back now. Hopefully you paused and did the problem here. And so let's begin with K equilibriums, an equilibrium constant that's greater than 1. So remember, that's going to favor product formation, right? So that means we're going to have a negative delta G value. Equilibrium constant equal to 1, we already said that's going to be a delta G of 0. An equilibrium constant less than 1 is an unfavorable reaction. It favors starting material over product, and so the delta G would be positive for that reaction, because we're going uphill. We'd have to put in free energy into such a reaction to make it occur. So again, equilibrium constant greater than 1, a negative delta G value, and the reaction's favorable and spontaneous. Equilibrium constant equal to 1, delta G is 0, the reaction's at equilibrium. If we have an equilibrium constant less than 1, it's an unfavorable reaction with a positive delta G. Now this concept will become important as we see in class various types of reactions that are favorable or unfavorable. So I'll just give you an example of some reaction type and bond types that are spontaneous and strongly favorable, and that's hydrolysis of some type of high energy species is strongly favorable and liberates a lot of free energy. The equilibrium constant lies vastly in favor of generating those products. So here's one example, thioester. If we have this thioester, if we hydrolyze that with water to generate the carboxylic acid and the thiol, so cleaving this bond effectively, we're generating 2 molecules from 1. There's an increase in entropy. The carboxylic acid that's generated here is resonance stabilized, so that's a lower energy species. So again, we're generating free energy, we're generating negative delta H, increase in delta S, a negative delta G. A positive equilibrium constant vastly lies in favor of thioester hydrolysis for the products rather than the starting material. So that's useful to keep in mind, because this is often used to power other reactions. Another example you may remember from organic chemistry is the hydrolysis of an anhydride type structure. Again, just like a thioester, the hydrolysis generates 2 molecules instead of 1, so we get a carboxylic acid here and a carboxylic acid here, and those are each resonance stabilized, so we end up with an enthalpy negative delta H, release of enthalpy, and an overall strongly favorable hydrolysis reaction. And then the third example that you're probably familiar with is ATP. These phosphoanhydride bonds, like in this so-called gamma phosphate of ATP, is also hydrolysis of that is strongly favorable. So if we hydrolyze the phosphoanhydride, we end up with ADP, breaking this bond, and inorganic phosphate, just this group here. And because we're getting 2 molecules instead of 1, those are resonance stabilized, so we end up with a strongly favorable reaction, and the hydrolysis of ATP to ADP, or even 2 of these getting hydrolyzed to AMP, adenosine monophosphate, is often used to power other reactions, to provide the input energy for other reactions in biochemistry. So, to summarize, in this video, we learned the relationship between enthalpy, entropy, and free energy, the relationship between the equilibrium constant and the delta G, change in Gibbs free energy, and which types of reactions are strongly favored. And I'll just encourage you to test yourself with practice problems just of the type that we did so that you become familiar with making these predictions. Thanks.